We'll talk about WIMPs and FIMPs. Okay, just a bit of publicity for Javier. So he's Javier. Actually, he's now in Chile doing an internship with Roberto in Antofagasta. And that's it. Another thing, okay, I'm here. I'm far away from you guys, so 9 p.m. So I may not be very awake now at this time. We were far away, but you guys have to come here. We'll be super happy to host you. Okay, now let's go back to our business. So I don't think I have to convince you guys about the existence of dark matter. Just let me tell you a couple of things to settle the ground. So you know that there are these several observations that indicate the existence of dark matter. In particular, it's a missing gravitational force, right? And at very different scales. For instance, we have a scales of kiloparsecs of galaxies. We have the flat rotation curve of the galaxies. So in the scale of kiloparsec, but also a scale of megaparsec, the really clusters of galaxies. We have also the rotation curves. But we also have, for instance, the bullet cluster. So I think that you guys are familiar with the bullet cluster. So kiloparsec, megaparsec, but even the highest scale here. So it's complete. It's basically a very homogeneous map of temperatures. However, there are very small inhomogeneities, 10 to the minus 5 or so, that could be very well understood, explained in the framework of lambda CDM, this standard model of the cosmos, where dark matter, in particular cold dark matter, plays a fundamental role. So if you guys have any question, please stop me. No need to wait until the very end for questions. So please just raise your hand or open the mic and that's it. Of course, I'm Colombian, so I have to put at some point an arepa. So here's the arepa. So if this corresponds to 100% of the energy density of the universe, at present, 70% or so is in the form of dark energy, while 25, so 1/4 is in the form of dark matter, and we'll focus on dark matter, and only 5% or so is standard model, so baryonic physics. So only 5% of the present universe is kind of under control. The rest, 95%, like 70% dark matter, and the rest dark energy, and the rest 25% of dark matter. And that comes from exactly from this map of inhomogeneities of the CMB. Okay, so at this point, you're kind of convinced that dark matter is there. We don't know what it is. However, we know some characteristics. For instance, some properties. It has to be neutral in the sense of electric charge and color charge. Or if it has a fractional charge, it has to be very, very small. It has to be massive. It's dark matter, right? It's matter. And that means that it has to be non-relativistic at the moment of structure formation. It cannot have very strong interactions with the standard model because we have not detected so far. So weak interactions, I don't mean electroweak, just not very sizable interaction with the standard model. And that's because we have like evidence at very different scales, different time scales in the evolution of the universe. So, and the cool thing is that dark matter needs new physics beyond the standard model, because if you want a fundamental particle to be responsible for this dark matter, we don't have any viable candidate in the standard model. So that's cool of dark matter. So really the question that we want to ask or to want to solve is what is the dark matter? However, here we'll try to tackle this question in a slightly different way. It will be more, how was dark matter produced in the early universe? It's not exactly the same question. It will not be exactly the same answer. However, if we understand how dark matter was produced in the early universe, we will have information about some characteristics, so mass scales, typical couplings with it. itself or with the dark matter. So, but here, just to emphasize one thing, we want to understand how dark matter was produced in the early universe. And if I talk about the early universe, I want to have control of the early universe. How was the evolution of the universe in the earliest stages? So another question I will try to tackle is how did the early universe evolve, right? And that's because if we want to understand how it was produced, I mean, it was produced in a given background, so we have to understand that background. So in particular, how the universe expand, how the temperature evolve in the very early stages of the universe. Okay, so that's the plan of the day. So I will talk very briefly about WIMPs because I think you guys are very familiar with the WIMP mechanism. Once we understand what the WIMP mechanism is, it will be trivial to understand what the FIMP is. So WIMPs correspond to weakly interactive massive particles, while FIMPs correspond to feebly interacting massive particles. I will give some details about the FIMP paradigm. Then we'll discuss about cosmology. Cosmology of the early universe could be a standard or non-standard cosmology, could be like low temperature reheating, and how dark matter could be produced during these stages of an early matter domination or a non-standard cosmology, or simply in the case of low temperature reheating. And in general, we will discuss in general, however, we'll use an example. So I think it's the simplest dark matter model ever. So it's singlet-scalar dark matter. And we'll make the discussion in this particular scenario because it's easy and it's possible to generalize to more Baroque scenarios. And then we'll have the dessert that will be like the conclusions, right? Okay, so let's start with the FIMPs, the paradigm of WIMPs, weakly interacting massive particles. So I think I think you guys are familiar. Just let me stress some points. So the idea of WIMP dark matter is very simple and it's basically chemical equilibrium. Chemical equilibrium between dark matter and the dark sector. So you can imagine that we have these dark balls are dark matter, and this white one corresponds to standard model particles. And in the early universe, you can have annihilation of dark matter and creation of dark matter. So chemical equilibrium means that these two reactions happen in the early universe and happen at exactly the same rates, right? If the rates of production and annihilation are the same, that means that dark matter reaches chemical equilibrium. So here, for instance, I'm showing a plot of the co-moving number density as a function of the inverse of the temperature. So if you want to time, so this x of the inverse of temperature is a proxy of time. So time is flowing from left to right. So this blue line here corresponds to the equilibrium density. So Maxwell-Boltzmann, Fermi-Dirac, whatever you want. So dark matter, the number is dark matter is tracking the equilibrium. So is the black line. However, at some point you break equilibrium, you break chemical equilibrium. You say that dark matter freezes out, and after the freeze out, you reach a plateau. You reach a plateau, and that's why that's how the observed dark matter abundance is produced, right? So you're in chemical equilibrium, you break this chemical equilibrium, and you have the WIMP paradigm. So DP typically requires cross-section at the picobar on the electroweak scale. So few 10 to the minus 26 cubic centimeter per second, that's around the picobar. And couplings and masses, again at the electroweak scale, so GV to TV masses, and couplings of order 1, 10 to the minus 1, something like this. One important thing is that as this dark matter reaches equilibrium, this is independent on initial conditions. So independent of the reheating temperature, coupling to the inflaton, the dark matter density after reheating, blah, blah, blah. In general, all the cosmological evolution before the freeze out. And that's because the equilibrium acts as an attractor. So once you reach the attractor, you completely lose all the information about initial conditions. Okay. So this is very, 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 very nice. It's a very compelling scenario. However, we have been looking for these WIMPs in the last decades using this multi-channel and multi-messenger approach. but there's no compelling detection so far. And what's the idea of FIMP? So if we have this reaction in the early universe, so annihilation and production of dark matter, you can imagine that using the same reaction, you can have annihilation of dark matter into a couple of standard model particles. And you can look for these standard model particles in satellites or in detectors on the ground here, so at Earth. That's basically the indirect detection. You can look for dark matter annihilating or decay into electron positrons, into photons, into neutrinos, into antimatter, and you can try to look for these annihilation products, for instance. You can also have direct detection, which is basically elastic scattering of dark matter with standard model particles, so with nuclei or with electrons in the detector, and you can look for the signals of this elastic scattering. And you can also have proximate colliders. So for instance, the LHC, you can have PP into a couple of dark matter, so missing ET and a monophoton, mono something. But you know the story, right? So we have been looking for these WIMPs intensively, and there's no detection so far. So I think it's fair to say that WIMPs, at least the standard or the vanilla version of WIMPs, is facing some tension because of non-observation. So where is WIMP? It's not dark matter, right? We can imagine other production mechanisms beyond the WIMP mechanism. For instance, the FIMPs. So let's see what FIMPs mean. So FIMPs stand for Feebly-Interacting Massive Particles. And if you understood the idea of WIMP, so the idea of having equilibrium, tracking equilibrium at some point going out of equilibrium, the idea of FIMPs is basically is very similar. So if WIMPs, you want equilibrium, so these two reactions to happen at the same rate. In FIMPs, you want the opposite. You want to avoid having chemical equilibrium. And how can you avoid that? Okay, you can imagine that these two reactions can happen. However, you don't want them to happen at the same rate. So you want basically dark matter to be produced, right? But you don't want dark matter to annihilate. So in the FIB mechanism, dark matter is produced but never efficiently annihilates. So if this dashed line corresponds to the equilibrium density, these solid lines correspond to the actual dark matter evolution. So dark matter is produced despacito, suave, suavecito, and at some point it freezes in, right? And you reach a plateau without tracking the equilibrium density, right? So dark matter is never in equilibrium, in chemical equilibrium. However, you don't care about that. You're just producing dark matter via the FIMP mechanism. So what does the FIMP requires? So you want to avoid thermalization between the two sectors. So you need very suppressed portals, very suppressed interaction rates between the two sectors to avoid thermalization. Okay, that means
Nicolás,
that yes.
Nicolás, can I ask you? So then this
yes,
plateau saturation regime occurs when the expansion rate is it becomes comparable with the this balance between production and annihilation. What is the origin of this
No, because okay,
plateau?
that's the reason you freeze out. So when you have freeze out, so this moment here is basically when H is of the order of the expansion rate is of the order of production rate. That's a freeze out. Here is not the same because here H is always much bigger than gamma, always.
Feebly, okay. Feebly,
exactly.
because feebly. Yeah.
Exactly.
And
here, the scale of this plateau is where the temperature is of the order of the mass, either the mass of the mediator or the mass of the dark matter. Yes, it's basically because you have the thermal plasma does not have enough energy to produce. So it's basically a kinematic condition. You cannot produce it because there's no energy anymore.
Okay, yeah, I see. This is a kinematics purely. Okay, yeah.
Exactly. Yes.
Thank you. Yeah, understand.
Thanks. So here we are not confined to the electroweak ballpark. We can have masses basically higher than the KV because Lyman alpha, but it could be up to Planck scale, basically. And here we're not tracking equilibrium, so it will depend on the initial condition. So that's important. Typically, people assume a dark sector which had a negligible initial population. This you have to be super careful because during reheating, for instance, you can produce dark matter. During inflation, even you have always this gravitational particle production. So here for films, that you have to be careful because it does depend on the initial condition. Okay, so the films come in two versions, the infrared, and this corresponds to what Sergey was asking. So in this case, the production happens when the temperature of the plasma is of the order of the masses. Masses of the mediator, masses of medium. In the infrared version of films, you want to have renormalizable operators. And renormalizable operators means that you will have to have very small couplings, portal couplings between the dark sector and the visible sector. And like typical numbers is 10 to the minus 11. So very small portal couplings. This could be unnaturally small, right? 10 to the minus 11. You're not happy with this number. However, it could be technical natural in the sense of thought, right? So stable under relative corrections. And the model that will show you present is technically natural in this sense. So it will stay small, even if you take into account the corrections. Okay, what about detecting themes? Well, by construction is very complicated, but you cannot complain because you want to have to avoid thermalization. That means you need to have small interaction rates. That implies small couplings, and you have small couplings, small cross section is difficult to detect. Surprise, surprise, right? However, it's not hopeless. Even if you have very small couplings, 10 to the minus 11. There are different techniques or different ideas. For instance, you can have light mediators. If you have a very light mediator, even a massive mediator, you can boost your direct detection signal, right? Or you can also go to light dark matter, MEV in the MEV ballpark. And the idea here is if you reduce the mass, you have to increase the number density of dark matter. So you're boosting like the flux if you want. So it's like in the collider if you increase the luminosity. So light mediators or light dark matter. And yes, and also there's a big effort for trying to detect light dark matter in the MEV ballpark, especially in direct detection if you're looking for elastic scattering, not with nuclei, but with electrons. That way you can reduce during this search, you're typically not looking for the dark matter, but looking for mediator coupling. So mediator will have a displaced vertex. Or even you can detect this guy in phaser or in Matusla. So really having long-lived particles. So there's idea not really testing film dark matter, but models with films. Okay, good. If you have no questions, I would like to say some comments.
Yeah, one question, Nicolás. And
Yes, please.
these simplest models of a dark sector based on dark photon as a mediator, it looks very similar. At least I don't know how close this model to FIMP paradigm. Dark photon is also in this ballpark of. I mean, masses, mediator.
Yes.
Oh, I don't hear you. I don't hear you. I don't know if it is a problem of my internet.
I don't know. Can you guys hear me?
I also have
No, no, I can hear you. Yeah.
No?
No, I can hear you now.
Okay, now it's working.
Uh-huh. Okay. Yeah, this is
it
my
working?
question. Just
But wait,
okay.
can you hear me?
Yes, I can hear you.
Yes, we
Okay.
can hear you a little bit, but we can hear you a little bit.
Mm-hmm.
Maybe
Oh,
you could put higher than your microphone, please, Nicolás.
is it better now? I increased the mic. Now it's a maximum, the mic.
Yes, it's not.
Okay, yeah, it's okay.
Okay. So yes, so exactly this model, this left panel here corresponds to the dark photon. So here they're assuming a massless dark photon. Yeah, so it's exactly this is like dark QAD, right? So this is like a light fermion, and the mediator is a massless dark photon, and this kappa corresponds to the kinetic mixing.
Uh-huh. And yeah, so then the portal is should be very weak in order this paradigm works, right?
Well, not very big, very small. 10 to the
You know,
minus 10.
yeah, of course, very small. Yeah, this is
Yeah.
very small. And
Exactly.
then how it is comparable with the existing limits or on epsilon? Are the experimental accelerator fixed target limits, for instance, from an A64 are
Yes,
comparable?
there are a lot. Yeah, but typically are you can probe, but not as not 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 that small for the kinetic mixing.
Uh-huh,
Yeah.
uh-huh. Yeah. Okay. Okay. Yeah. Thank
Okay,
you. Thank
thanks.
you, Nicholas. Yeah.
More questions, comments? Okay, so I will make a point on the cosmology. So standard versus non-standard cosmology. So first, what do I mean by standard cosmology? So what we know actually is that at the BBN, so when, at the moment of Big Bang nucleosynthesis, means when the temperature of the universe was around few MeVs, the universe was dominated by standard model radiation, right? And we have a conservation of the standard model entropy. So that's what we know. I mean, the earliest information that we have of the universe. So what standard cosmology means is we're doing a very dangerous extrapolation up to the reheating epochs. So where the temperature of standard model was what, I don't know, 10 to the 10, something like this, maybe more. So, but it's really an extrapolation. So we assume in this 13, 15 orders of magnitude that we are making the extrapolation, that the standard model entropy is always conserved, and that the early universe was always dominated by standard model radiation, right? That's a typical assumption for the cosmology, right? And on top of that, we kind of assume an instantaneous reheating. So reheating is during inflation, the universe is dominated by the inflaton, and this energy has to be transferred to the standard model. And this process of transfer of the energy from the inflaton to the standard model is the reheating. So the reheating could be fast or slow, but it definitely not instantaneous. So there's a period where the universe is dominated by the inflaton, but they're slowly creating the standard model, maybe because of due to decays of this inflaton, right? However, please keep in mind this is an extrapolation, and we have really this is not guaranteed by no meaning, right? So it makes sense to, I mean, as we don't know how reheating and how the early universe behave, it makes sense to make this kind of uh, of of assumptions. However, it's an assumption, right? It's an extrapolation that we are doing. The simplest model. So it's not the standard by any means. It's just the simplest assumption that one can do. So I think it's kind of pretty much the common law in particle physics that we have the inflation, So during the universe was dominated by the inflaton, and we have an instantaneous transition from a universe dominated by the inflaton to a universe dominated by standard model radiation. And after that, I mean, the temperature scale like 1 over the scale factor, and that's it. In the terms of temperature, or in the term of energy density, with the same thing. The universe during inflation is dominated by the inflaton, and you have an instantaneous transition to a universe dominated by radiation, and then the standard model radiation takes scale like T power 4. That means that A scale factor power minus 4. However, in general, we expect the reheating to be something much more complicated. So again, this will correspond to an epoch to inflation, right? Energy density dominated by the inflaton. So this is the energy density as a function of the scale factor. So time is flowing from left to right. So we have inflation here. So we have an era of radiation domination, right? But there's also an intermediate era, which is the reheating. So during reheating, the universe is dominated by the inflaton, so this blue line. However, you start to create the standard model. You start to create photons and the standard model particles, because of the inflaton is typically decaying into standard model. So you can imagine that inflaton decaying into a couple of standard model particles. Yeah. So the inflaton, you're losing energy because you're transferring energy from the inflaton to the standard model. So during reheating, we don't know what the equation of state of the inflaton. We don't know what the equation of state of the universe in general, and we don't know how the temperature scales with the scale factor, right? It will not scale as free radiation because it's not free. We have a source term. The inflaton is decaying to radiation, so it's pumping energy into the visible sector, and therefore we don't expect the temperature to scale like 1 over the scale factor. So the reheating could proceed via decays or via nature of inflaton into standard model, and it's a continuous process, and it's typically not instantaneous. So one typically has to solve the Boston equation for the background, meaning the Boston equation for the inflaton energy density and the Boston equation for the radiation energy density.
Nicolás, one question.
Yeah,
and recall me, please. What is the coupling of the inflaton with the standard model sector? What is the coupling and how it is?
So yes, we have no clue, huh? So we could imagine that the inflaton decays, so we have a perturbative decay, but that's always an assumption. And of course, if you fix the characteristic of all these guys, spins, mass, and all that, you can compute the decay width. This is a two-body process, 1 to 2, a decay, and it depends on what the reheating temperature. So the reheating temperature is the onset of radiation domination. So when the first moment where radiation starts to dominate. So if you have gamma, you can, so the decay width, so you can compute what's T reheat. Yes?
Yeah. What are the theoretical ideas on this coupling?
So it really depends, right? So yeah, so if it's kind of big, it will decay very fast, so you expect a very high reheating temperature, but it could be a very long-lived, of course, 1 second, right? And therefore you could expect a small reheating temperature, and that's basically the idea that I will pursue here.
So this is model dependent.
It's completely model dependent. We don't know how the question of the inflaton. We don't know if it decays, if it annihilates. Typically, in the reheating, you have this non-perturbative effect. You have gravitational particle production. It's typically a mess. But there are some scenarios where you can compute everything analytical, linear, yeah. But if you're picky for solving your heating, you have to go to lattice. And that's another universe.
Yeah. Okay.
Thank you. Thanks for the question. Okay, that's the case of reheating, but we can also imagine non-standard cosmology. And non-standard cosmology could be triggered basically by a heavy particle. So in non-standard cosmology, you can imagine simply a case of early matter domination. And these early matter dominations are, from particle physics, from the model building, are trivial to construct, right? You just need a heavy guy with a lifetime long, I mean, could be a second, right? So long enough. And if you think you can have these guys, I mean, you have moduli in string frameworks, or you have got theory, you also have a candidate for this, or even you have just right-handed neutrinos, right? If for leptogenesis, you need a right-handed neutrino, mass, I don't know, 10 to the 10, something like this. It could be long-lived, yeah. And bingo, you can trigger an early matter domination, but you can also have, if in the context of primordial black holes, if you have very light black holes with masses in the ballpark of grams, kilos, or even tons, they will Hawking evaporate very early before the onset of BBN, and they could also trigger eras of matter domination, so primordial black hole domination. And we'll also, yes, see what happens if you have this kind of scenarios, right? So if you have early matter domination, you can have the universe dominated by matter, so different equation of state, and at some point it has to decay, so we'll have an entropy injection. Yes, exactly, that's the idea. So we'll discuss the WIMPs and FIMPs in the context of this non-standard cosmology. In the framework, a very simple dark matter model, which is the singlet-scalar dark matter model. And it's very simple. So on top of the standard model, we just have to introduce one particle, S, which is our singlet-scalar guy. We want it to be completely stable, so we impose a Z2 symmetry, just to make it stable. So the scalar potential will have a term for the quadratic term on the field that will give rise to a mass. We can also have a quartic, so will be a quartic coupling, so S power 4. And the only renormalizable portal is the Higgs portal. So we can imagine H squared, so two Higgses and two dark matter particles. And that's it, right? So we have three free parameters, the dark matter mass and the Higgs portal, and we focus on these two couplings. So mass and the portal to the dark matter, to the standard model, which is through the Higgs. And there's also a quadratic coupling, but for our case of WIMPs and FIMPs, it will play no role. So really we have, even the model contains three free parameters, we have two in reality for our phenomenological purposes. So we can study this model in the framework of the WIMP paradigm. So dark matter S could be produced from a standard model, for instance, to the Higgs portal, right? So here I'm showing you a plot of the couplings required for different masses. And this thick black line corresponds to the parameter space that fits the observations, right? So in order to have a WIMP dark matter, you need dark matter in the ballpark of GVs to TVs with coupling of order, say, 1, 10 to the minus 1, 10 to the minus 2. You can see, for instance, that here, this corresponds to the Higgs funnel. So when you have a resonant production of dark matter to a resonant S-channel exchange of the Higgs. So this peak here, and this corresponds to kinematical threshold. Yeah, if dark matter is heavy enough, you can start annihilating into Z's, into W's, into tops, and that's it. So this is the WIMP paradigm in this model. And as I told you before, and as you know, so the WIMP is under siege, if you want, because they're suffering from very strong experimental constraints. And all these bands here correspond to experimental constraints. We have constraints, for instance, for the invisible decay of the Higgs, this one, and the others basically are direct detection. With electrons, this one, and with nuclei here, and you can see that basically only very heavy parts of the parameter space survive all the experimental constraints. So that's kind of sad for WIMPs. However, this is not the only mechanism. We also talk about FIMPs. Now it's FIMP dark matter. It's exactly the same model, right? Now for FIMPs, again, this is the parameter space. This thick black line corresponds to the parameter space that reproduces observations for dark matter being produced via the FIMP mechanism. As I told you before, you need very small couplings, 10 to the minus 10, minus 11, minus 12, and a very large range of masses. So MEVs here to TVs, but I stop here, but I mean, these lines continue, right? So it will have continued here to even more, to heavier dark matter states. So it's exactly the same model, just that I'm changing, I'm decreasing the coupling from order 1. I have WIMPs to 10 to the minus 11, I have FIMPs. So these two plots, so this one and this one, I presented exactly in the same parameter space. So exactly the same. So this thick line here correspond to WIMP solution, and this one correspond to FIMPs. So for the masses that we discussed previously, so WIMPs in the GV to TV scale, FIMPs much larger range, WIMPs couplings order 1, FIMPs couplings order 10 to the minus 10, minus 11. So we have these two solutions correspond to these two thick black lines. All this parameter space is not good because we are overproducing. So if you want too much dark matter, and here above and below is not enough. So really in the standard cosmological scenario, these two lines are the only viable parameter space. However, this is true if we assume that we have standard cosmology, and high reheating temperature, meaning that dark matter was always produced during radiation domination. And this is exactly the same Boltzmann equation that we showed you before. The solution for WIMPs, you track in equilibrium, and for FIMPs, you produce dark matter, and at some point you freeze in. But if I start you see that we have different evolution of the dark matter yield. So again, this is for dark matter have to be produced earlier. So the freeze out has to happen earlier. You have to overproduce because you have entropy injection, and entropy injection will dilute what the repolation of dark matter. So you need a more efficient WIMP and FIMP mechanism. And what does that mean? So it is exactly the same parameter space as before. The thick black lines here correspond to WIMPs. The thick black lines here correspond to FIMPs. In assuming a high temperature reheating, if I start decreasing the reheating temperature, 10 to the 12, 10 to the 9, 10 to the 6, 10 to the 3, 10 to the 0 GV, so I'm decreasing. So I can explore all this parameter space that previously was completely ruled out because dark matter overproduction. So first message, the parameter space that was excluded because of overproduction becomes allowed once you decrease the reheating temperature. 1 point. Second point, we say that these WIMP and FIMP were two completely disconnected scenarios. However, if you decrease the reheating temperature, you can continually go from one to the other. For instance, in this case of 4 TV, sorry, you have that you can continuously go from one to the other, right? So if you have, for instance, this T reheat, this will be the line that fulfills observations, right? And of course, you need the T reheating to be higher than TBBN, so this parameter space will not be allowed. Another thing is that this thin dotted line corresponds to the border between WIMPs and FIMPs. That means that above this line you have thermalization, and below you don't have thermalization. So you can see that current constraints are already testing large parameter space that are favored by low temperature reheatings. And we're also testing, for instance, this chunk of the parameter space, we're also testing the FIMP paradigm with low temperature reheating, right? But that's very interesting because direct detection is already testing and excluding chunks of the parameter space favored by the FIMP mechanism. Okay. I'm very late, so I have to hurry up a bit. That was for one particular cosmological scenario, assuming one particular characteristic of reheating. Here it's basically the same exercise, just changing what we assume of reheating, how reheating proceeds. But the information is basically the same. The parameter space that was where you have dark matter overproduction becomes viable, and you can continuously go from one to the other.
Nicolás, excuse me, at this point.
Yes, please.
So then this reheating temperature should be as a free parameter in the game, as a cosmological parameter to probe with you, to test, as you said, because
yes, here we're assuming
well,
right. We are assuming it's a free parameter. However, if you have like a full model of reheating, you can compute what's the reheat. For instance, if you know what is the mass of the inflaton and what are the couplings to the standard model, that's it. You compute it.
yeah,
right?
but then this temperature would be related to other parameters of the cosmological model. So then
Exactly. Yes, that's correct.
So then in the game there is at least one cosmological parameter, right?
Yes.
Which is yeah.
So what I'm really assuming here is the equation of state omega of the universe during reheating. So the equation of state during reheating. So that's one thing. The other is how the scaling of temperature minus one parameter, alpha, whatever. Let me put this alpha. So how the temperature scales during reheating, and what is the reheating temperature? This is really the three parameters that I'm using. Of course, these are I mean, this is an effective approach. You can parameterize within these three guys. However, you have a full setup, you can compute that. Yes.
Yeah. But in that full setup, there will be a parameter, free parameter, which mimic this
For instance, you can have the
effective,
mass of the inflaton.
effective parameter. Yeah, right.
The
Like a mass of
inflaton, the couplings of the inflaton to the standard model, and that's it. Yes, yeah.
But they enter into the game via this effective parameter, which is reheating temperature.
Exactly.
Right?
Yes.
This is what I just
Yes.
wanted to clarify.
Yes,
Okay, thank
exactly.
you.
If you want to compute T reheat, you basically take this H
Sure.
equal to a T reheat.
Yeah.
Right? As usual.
Okay. Yeah. Thank you.
And with this, we could do exactly the same, not assuming a low temperature reheating, but assuming an early matter domination. And this early matter domination, remember, is basically what I told you before. So you can have a heavy guy with a large lifetime that dominates eventually the total energy density of the universe. So, or you can also have the scenario where you have primordial black holes, right? Like that's you have to have Hawking operations or production of dark matter is another source, but that's a possibility. So again, this is the same parameter space. Higgs portal as a function of the dark matter mass. This thick line is the WIMP. This on top is WIMP. On down here is the FIMP. And you can go from one to the other. So all this parameter space between these two lines that was excluded because of overproduction becomes viable. And you can continually go from one to the other, playing again with the cosmology. I don't have much more time, no, Antonio? I've been talking
You
for
have time, Nicolás. We have some flexibility. Nicolás has a question.
Okay.
These different stages, I suppose stage 1 should be inflation, stage 2 is radiation
No,
domination area, or this
no,
stage
no,
in
no.
the
Sorry.
low.
Yes. So I didn't explain that. Sorry. Here I'm focusing on early matter domination. So what they call stages 1, 2, 3, and 4 correspond. So stage 1 is the radiation domination standard. Stage 2 and 3 correspond to early matter. And stage 4, adiabatic.
Nicolás,
Uh,
Nicolás, can you repeat because that cut.
Yes, Nicolás, we didn't hear you clearly. Please, can you please repeat this explanation for the different stages?
okay, okay. So yes, maybe it's my mic. So I was saying that stage 1 is radiation domination, early radiation domination. Stage 4 is radiation domination again, so these late times. Stage 2 and 3 is really early matter domination. However, the difference between stage 2 and 3 is that stage 2 is adiabatic and stage 3 is non-adiabatic. Yes? What's the difference between adiabatic and non-adiabatic is that in the first stage, in stage 2, the matter is dominating. However, it's not effectively decaying into radiation. So that's why, so the temperature is always scale like 1 over the scale factor. So it's dominating, but it's not decaying. In stage 3, it's not adiabatic because it's really decaying. It starts to decay. Yeah. So start to decay, start to inject entropy in the standard model, and therefore the radiation is not free radiation, and it's not free because it has a source term. This guy who is dominating is decaying into radiation. Is pumping energy into the visible sector. So these are the stages. Yeah. Thanks for the question.
Nicolás?
Yes. Yeah.
I'm a bit still confused with this concept of early matter domination. Yeah. But in the very early times, you have radiation dominated universe, and then later on you have matter dominated universe. And this is a period which is like in between two radiation. Yes. Is that there?
Yes. So this early matter domination is not the one of the quality, right? So the late dark matter domination. Just imagine that you have a heavy guy. I mean, you agree that if you have a non-relativistic guy, it will tend to dominate because its energy density go like 1 over scale factor cube, while radiation goes like 1 over scale factor power 4. So matter tends to dominate, right? That's why dark matter dominates in the late universe. So you can imagine that, but this guy has to decay at some point. And that's the idea of this early matter domination. It's really before the quality. So it's really before BBN.
Okay, so when it decays, it's like pumping all the entropy and energy into radiation again, and then you have radiation domination.
Into radiation, exactly. Yes. Then you have the radiation, exactly, radiation domination. Yeah.
Equality of radiation.
Yes, I can continue here. No, I cannot. So after that, they have again matter domination. It says dark matter domination, and then cosmological constant. And there's where we are.
Okay, thank you.
Yes, thanks.
So you're talking about times which are much earlier than say the typical,
Right. Yes. So this early matter domination has to finish before the onset of BBN. BBN. This has to be a temperature higher of temperature of BBN. Yeah. So it's really early times. Yeah. Thanks. Yeah. And I just want to, yes, maybe along what Sergey was asking. So here we have done, I have two more slides, sorry. An effective approach to this cosmic reheating. So the reheating, we parameterize in this way. So using the equation of state omega of the inflaton during reheating, and a parameter alpha that for us is encodes how the standard model temperature evolves during reheating. So typical parameters is, okay, and here I'm showing you a plot of alpha. So how the temperature scales as a function of the equation of state of the universe during reheating. And this dot here and these crosses correspond to different models in the literature that you can find for reheating. For instance, this maybe is the usual suspect. This corresponds to an inflaton, a massive inflaton that decays into radiation. So it's a matter, so equation of state 0, and it decays into radiation, alpha is 3/8. But there are other models, for instance, kination. You can imagine an era of kination, and in that case, omega and alpha are equal to 1. But then you can also imagine inflatons decaying or annihilating into fermions or into scalars, but that are not oscillating during reheating at the bottom of the quadratic, but to the quartic potential, or powers 5 power 6 power 8, and therefore you can explore different values of the equation of state at different values of alpha. Yeah. So just to motivate that reheating could be, I mean, once you fix a model, you can compute all these parameters, and I mean, the possibilities are very large, right? So all what I showed you before will change as a function of the characteristic of reheating. Okay, and this was done with Marta Lozada, that you may know her, and Kuldeep Dekha, which is a postdoc here working with us. And it's interesting to study this kind of planes, alpha as a function of omega, because this is the last slide. So because here I'm showing you the maximal temperature that could be reached for a WIMP. So in radiation domination, WIMPs have to be lighter than, say, 100 TeVs or so because of unitarity. However, you start playing with the cosmology, with low temperature reheating, you can evade these strong unitarity constraints. And for instance, here I'm showing you isocontours of the maximal mass that you can reach. So for instance, you can imagine WIMPs of 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 10 GeVs, 10 to the 14 GeVs. So super heavy dark matter that could be produced even in the case of WIMPs. Standard WIMPs, you're not playing with the particle physics, but with the cosmology. So it is a way of exploring very heavy dark matter particles, just changing the background, the cosmology. Okay, and that was the last thing I wanted to tell you guys. Do you have, Sergey, a question? I see your camera on. No? Okay, good. So, postre, conclusions. So the first part, I think you are convinced of that. So dark matter exists. Its nature is still unknown, and understanding dark matter is one of the major problems of particle physics and cosmology. So how was dark matter produced? We don't know. However, there's a big prejudice for the points that supports WIMPs in general. And I think the WIMP paradigm during radiation domination is by far the favorite scenario. However, I just want to emphasize that there are many other models, particle physics models, for instance, with FIMPs, but also SIMPs, axion, ALPs, blah, blah. So there are very different directions. So one is really particle physics, change the particle mechanism for producing the matter. That's one option. However, you can also change the cosmology, right? You can also play with the cosmology and you have a huge freedom. You can explore, for instance, non-standard cosmologies, like early matter dominations, kinations, all this. But also you can play with low temperature reheating. That's completely viable possibility. And this non-standard cosmology, for instance, on low temperature heating could be triggered by particle physics, but also by cosmological or astronomical things like this. So just to emphasize that this non-standard cosmological scenario drastically changed the standard picture. So that's a freedom that we have, and therefore it has to be studied. So non-standard cosmology provides a smooth transition between different thermal and non-thermal mechanisms. For instance, we saw here that we can have smooth transition between WIMPs and FIMPs, right? And in general, non-standard cosmology relaxes the strong experimental constraints on thermal dark matter, on WIMPs, and increase the detection chances of non-thermal dark matter, as in the case of FIMPs. That's what we saw. And that's it. Thank you very much, guys.
Thank you very much, Nicolás.
Thank you.
Very nice talk. Question from the audience? Sergey, you had a question?
No, it's okay. I asked all the questions on the way. Thank you, Nicolás. Very clear.
A very nice seminar.
Yeah, absolutely.
Any question from the audience?
Thank you, Nicolás.
Thank you, Claudio.
Then my regards to Marta, I suppose he's here, right?
Yeah, well, she's not attending, but yes, I can pass the message.
There are no more questions. Mr. Nicolás for the very nice talk. Thank you so much, Nicolás.
Thank you. Thank you.
Thank you, guys. Sorry for my connection. It was messy a bit.
No problem. Thank you so much, Nicolás. We meet in the seminar.
Yeah, so thank you. Thank you. Bye.
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 Bye, everybody.
Bye.